Taking a look at our homework from last night, page 550, we want to do both of those questions. Question number 1 says, find the net electric field at a point 2.1 meters to the left of the 1.5 times 10 to the negative 6 coulomb charge in figure 11.9. This is figure 11.9 right here. We want to find the net electric field at this point, somewhere over here, point X we'll call it, 2.1 times 10 to the negative 2 meters to the left of that charge A. All right. There could be something there. There could be an experiencer there at point X, although if there is, we certainly don't know anything about that experiencer. If there is something at that point X to experience the field, we clearly know more about what's producing the field. In fact, we know more about both things that are producing the field at point X. We get two positive charges that are making the field there. We have a field caused by A that points to the left. And it points to the left, electric field A, because it points away from a positive producer. And immediately to the left of a positive producer, okay, away from it is going to point to the left. Now, charge B is also a positive producer. It produces a field like this, but to the left of charge B, a positive producer, it's once again going to point to the left. So both of these things are going to point to the left here. We've got to find both of those fields, the values of both of those fields, and then we've got to add them up, making sure that we make them both either negative or positive, both the same sign anyways. You guys clear on why those are both in the same direction there? Both to the left? Any issues as to the direction of those fields? Because we can't go any further if you're having trouble determining what the direction of the field is. You can do all the calculations you want, but if you can't determine the direction, those calculations are meaningless, right? Let's calculate the value of EA. Electric field A, or at least the magnitude of electric field A, is going to be KQA over R squared. It's 8.99 times 10 to the 9 times the charge of A, which is 1.5 times 10 to the negative 6. Be careful here because they'll often give us microcoulombs for units as opposed to coulombs. Give me a bit of a break in this question. The distance would be 2.1 times 10 to the negative 2. And that's going to be in meters. Don't forget to square that. What do we get for EA, the electric field caused by A? 3.67 times 10 to the 7. And that would be newtons per coulomb, right? Agree with that? Yeah? Yes, Austin? Okay, good. Let's find the electric field caused by B then. It's going to be KQB over R squared. And you got to be really careful about this one. K, of course, is 8.99 times 10 to the 9. QB is 2 times 10 to the negative 6. What's the value of R here? What value of R would we use here for electric field caused by B? Yep. Good. 5.4 times 10 to the negative 2. Jacob, where'd you get that value? Yeah, R stands for the distance from the charge to wherever it is that you're trying to find the field, from the producer to where you're trying to find the field. The distance is not 3.3 or 2.1. The distance from charge B to that point is the sum of those, 2.1 plus 3.3, or 5.4 times 10 to the negative 2. Jacob, do you have the number for electric field B there? 6.16 times 10 to the 6 newtons per coulomb. Can anybody suggest to me why that EB is a smaller number than EA? I mean, if I'm looking at this ahead of time, I'm not going to know exactly what EB is, but I would predict that it's going to be a smaller number than EA. How come? The bigger charge, right? If it's a bigger charge, shouldn't that give me a bigger electric field, not a smaller one? Yeah, it's a bigger distance. Now, if you have a bigger charge, which should increase the field, and a bigger distance, which should decrease the field, which one matters more? Which one matters more? Distance, right? Distance, because we end up with a smaller field. Why does the distance matter more? Hugh? Because you're squaring it. You're not squaring the charge, right? You're squaring the distance. So it's going to matter more clearly here. All right. We're going to combine these. Now we're going to just say the electric field at that point, dropping the absolute value signs now because we are paying attention to direction now. We're going to say negative 3.67 times 10 to the 7 plus negative 6.16 times 10 to the 6. And we should get negative 3.67. Is that right? That's not right. What do you guys get, like 4.2 or something? Yeah. 3.67, what'd you get? 3.057, anybody else get that? Okay, so 3.67, Nikki gave me the final answer, I guess. 3.057 times 10 to the 7. And when you add those up, you should get negative 3.67 times 10 to the 7 newtons per coulomb. Could we have made those positive? Sure, right? Sure, we could have made them positive. We made them negative because that's typically what we do, make left negative. But in the end, if they're both in the same direction, you can really make them whatever you want, as long as you're clear to yourself on what that means, what that sign means. Right? All right, let's take a look at question number 2 now. It says an electron and proton are this far apart, 5.29 times 10 to the minus 11 meters, in a hydrogen atom. What's the net electric field at a point midway between the charges? Here's my electron. We'll call that charge 1. Here's my proton. We'll call that charge 2. The electron has a charge of negative 1.6 times 10 to the minus 19 coulombs. The proton is positive 1.6 times 10 to the minus 19 coulombs. We want to find the electric field strength midway between. This is kind of like the example we did yesterday, right? Except it wasn't an electron and a proton yesterday. The distance, by the way, 5.29 times 10 to the negative 11. Remember here one day we were calculating electric forces between protons and electrons in a hydrogen atom, and we found the electric force was really, really, really big. It was massive, in fact. Why was it so big? Well, it came down to this distance, right? If you square that distance and it's on the bottom, that's a big number. Well, it's a small number, actually. But if it's on the bottom, that gives you a big number for electric force. The closer things are together, the bigger the value of the electric force. That's why we got such a big number. All right, let's look at the field caused by the electron. Fields point toward electrons. So we're going to say E1, the electric field caused by the electron, is to the left. And we're going to say E2, the electric field caused by the proton, is also to the left, because electric fields point away from positives, toward the negative, away from the positive. So we're going to calculate the value now of E1 and E2, and then we're going to add them up, and we're going to add them up both as negative values, just like we did in the last question here. E1 is KQ1 over R squared, which is 8.99 times 10 to the 9, times 1.6 times 10 to the minus 19. We're dropping the sign of the charge, as we always do. And R would be half of 5.29 times 10 to the minus 11, right? What's that? 2.645 times 10 to the minus 11? And we got to square that. What do we get for the electric field there? You know what? I'm going to go out on a limb here and say it's 2.05 times 10 to the 12 newtons per coulomb. Now, E2, we could go through that process again for calculating E2, but I know it's going to be 2.05 times 10 to the 12 because all the numbers are the same. And then when we go to add those up, we're just going to say E, the electric field, net electric field, is negative 2.05 times 10 to the negative 12, 10 to the positive 12, plus negative 2.05 times 10 to the positive 12. And we end up getting negative 4.11 times 10 to the negative 12, 10 to the 12. Now, I drew the electron on the left side, the proton on the right side. So my answer doesn't really mean left. My answer means left with the way that I have it drawn, which is technically toward the electron. Had I drawn it the other way, I would have gotten a field that was to the right, but it still would have been toward the electron. That's why they say that here. Good. All right, I want to take a look at a few multiple choice questions here, right? The ones that I want to look at, start off, question number 44. I'll give you about 30 seconds to work on this one at your desks. Okay, should go pretty quickly. What's our answer to question number 44? What do you know, first of all, about X and Y in general, based on the shape of this electric field diagram? Forget about positive, negative. What do we know about, in general, these two charges? Yep. We know that they're repelling each other because the field lines are not joining up. If they repel each other, they got to be like charges. Right, Nick? They got to be like charges, either positive or negative. Now, which is it? Positive and positive, or negative and negative? Olivia, which is it? Why do you say negative and negative? Good, because the field lines are pointing towards both of them. Good. Let's have a look at question number 46 now at your desks. This one says 2 particles 1 and 2 of equal mass have opposite charges. The negative charge on particle 1 is 3 times greater than the positive charge on particle 2. So let's keep this straight now. They've got it labeled negative and positive. That's a good thing. But we know that if this is Q, if this one's Q, then this one would be 3Q. It's 3 times the value of the charge on charge number 2. The particles are placed 9 centimeters apart. We want to find the electric field halfway between the parallel plates here. So we want to find it 4.5 centimeters to the right of charge number 1. Let's draw the electric field caused by the negative charge. Okay, it's going to point toward the producer, so it's going to point this way. We're going to say E1 is to the left, and charge or field number 2 is going to point away from the positive producer, so it's going to point to the left as well. Make sense? Now, I've got those drawn both the same length. They shouldn't really be drawn the same length, right? Although in the end, it doesn't really matter for this question. If they're both to the left, then we know the answer is going to be toward the left of the page. But really, I should draw E2 about that long. How come? Why is E2 drawn about the third the length of E1? Yep. Good. Its charge is 3 times smaller. If we say E1 is my original field, KQ over R squared, then I'm going to say E2 would be K times, well, it would be a third of Q, right? Because it's a third the value of Q divided by R squared, which means the electric field 2 is 1/3 the original value, KQ over R squared. Now, that's not particularly important for this question, but if they happen to be in opposite directions, right? If E2 happened to be to the right, well, then we'd have to know which one was bigger, right? If E2 happened to be to the right, then the net field would still be to the left as a result of the bigger field, field 1. Does that make sense? All right, number 50. The intensity and direction of an electric field produced by an alpha particle, a distance of 5.0 times 10 negative 11 from the particle is what? Well, we have to know what the charge and the mass of the alpha particle are, or at least the charge of the alpha particle. It's on our data sheet. On our data sheet, it says the charge is plus 2e. What does that mean? Plus 2 times that elementary charge, or in other words, it's 3.2 times 10 to the minus 19 coulombs. So all we're going to do for this is say E is equal to KQ1 over R squared, 8.99 times 3.2 divided by 5.0 times 10 to the minus 11 squared. What do we end up getting there? Is it 1.2? 1.2 times 10 to the 12 newtons per coulomb. Is it toward the alpha particle or away from the alpha particle? It's plus 2e. It's a positive particle, so it's going to be away from the alpha particle, D. 51. All right, the magnitude of an electric field at a distance x from the point charge is this value. The distance is increased to 3 times the charge is reduced to 1/4 the charge. What's the new electric field? My original electric field is going to be KQ over R squared. My new electric field is going to be what? Well, K doesn't change. Q does. Q is 1/4 of what it was. Q over 4 or 1/4 of what it was. R changes to 3 times the value. If it was x, now it's going to be 3x, or 3r we'll call it. Becomes 1/4 over 9. Right? Remember to square the 3 because it's inside the brackets there. KQ over R squared. 1/4 divided by 9 is 1/36 of KQ over R squared. And we know the value of KQ over R squared Yeah, we're just trying to find that. 8.3 times 10 to the negative 4. So 136 of 8.3 times 10 to the negative 4. What does that work out to be? One of these two, right? D, 2.3 times 10 to the negative 5. Good. Okay, and the last one for now. This one's question number 52. All right, look at this question. It says we got all kinds of things going on here. What, 4 charges? 4 charges. And then we got a point P that's kind of in the mix there. What is it that's at point P exactly? We don't know. In fact, we're not told that there's anything at point P. We have to assume there's nothing there. So clearly, it's going to be a producer equation problem. We don't know if there's even an experiencer there, let alone information about the experiencer. So we're going to use producer stuff here. But you know what? Before we do that, let's see if we can simplify it a little bit. Let's draw some electric field arrows to see if anything cancels out and so on. Let's look at 3 and 4 first. I got a feeling about 3 and 4. 3 causes a field, it's positive. So 3 causes a field to the right, and 4 is also positive. It causes a field to the left. Those two are going to cancel out, right? The reason they're going to cancel out is because the charge is the same, the distance is the same. E3, the magnitude of E3 is going to be equal to the magnitude of E4. If that's the case, they cancel out. It's as if 3 and 4 aren't even there. All right, that's good. Okay, that simplifies things a bit. It takes away from the two-dimensional nature of this, right? Now let's look at E2. E2 is going to point this way, away from the positive charge, and E1 is going to point this way, toward the negative charge, charge 1. Now, I've got them drawn the same length, but should they be the same length? Should they be, Hugh? Yeah, why do you say that? Yep. Yep. Yeah. In the end, those electric fields are the same. Now, you can do that one of 2 ways. You can look at it and say, okay, I'm going to calculate the actual field value given the charge in microcoulombs, given the distances in meters, or I can just say little variable value changing thing. I can say E2 is KQ over R squared, and I can say E1 is going to be equal to K times 3Q, right? Because it's, sorry, 4Q, because it's 12 instead of 3. So it's 4 times the value of charge 2, and the distance is going to be twice the value of the distance between point P and charge 2. It becomes a 4 over 4 KQ over R squared. In other words, E1 ends up being the same value as E2. And since they're opposite directions, they're going to cancel each other out as well. It's as if those two aren't there as well. What's the answer to the question? Thanks, Nick. D. Got it? How many people got D for that one? Good, good. All right, today I want to go a little bit further with the electric fields, but not a ton. We've talked about the electric fields that are surrounding positive and negative charges. We've talked about the electric fields that's experienced by positive and negative charges. In other words, we've dealt with producers, we've dealt with experiencers. But in both cases, those have been what we call non-uniform electric fields. A non-uniform electric field is a field that's not constant everywhere. If we look at this electric field that surrounds this positive, of course, the shape of the field surrounding a negative would be the same. The strength of this field varies depending upon position. The closer the field lines are together, the stronger the electric field. The further apart they are, the weaker the electric field. Okay, you look at this, you could say that the closer they are, the closer we are to the producer, the closer the field lines are to one another. That means the stronger the field is going to be. And that should make sense to us, right? You get closer to what's causing the field, then the field is going to be stronger. You get further away from what's causing the field, then the field is going to be weaker. It's a non-uniform electric field. Today I want to look at a slightly different situation. Today we're going to have 2 conducting plates. Generally they're going to be metal. 2 conducting plates. One of them is going to be positive, one of them is going to be negative, although it doesn't really matter which one is positive, which one is negative. I want to draw the field lines that are caused by these 2 plates. We know the field always goes away from positive and toward negative, so we're going to draw a field line right here away from the positive toward the negative. There's also going to be one here, and here, and here, and here. What do you notice about those field lines compared to the field lines that we have in the positive producer that we've done over the last day or two? Yep. Yeah, they're all going in the same direction. In other words, they're all parallel to each other. If they're parallel field lines, then that means we have what we call a uniform electric field. A uniform electric field means that unlike this diagram, the electric field here is the same as the electric field here, which is the same as the electric field here and here and here. The electric field anywhere between those two plates is the same. The electric field here is completely different than the electric field here or here or here or here. In a non-uniform field, the field changes. The field varies, I should say, depending upon position. In a uniform electric field, the field stays the same. Now, this is a bit of a simplification because in reality, at the edges of these plates, you actually do have curved field lines. And at that point, you do have a non-uniform field. But what we concern ourselves with is the uniform field that's actually in between the plates. We're going to represent the electric field in this situation with parallel plates differently mathematically than we are this one. Okay, we can't represent a uniform and non-uniform electric field in the same way. And you're going to see exactly how that shakes down in just a minute here. You guys know that the electric field between two parallel plates is uniform. If we have a charge that's experiencing that electric field, then we're allowed to use the experiencer equation. This is not new. This is just review from what we've done over the last couple of days. There is a producer equation, E is equal to KQ over R squared, that we can also use when we have a non-uniform field. But it's only for a non-uniform electric field. That's E is equal to KQ over R squared. This one is valid if we have an experiencer, whether it's a uniform or a non-uniform electric field. In other words, it's valid in the first diagram and the second diagram. But the second one is only valid when we have a non-uniform electric field. In other words, it's only valid in the first diagram that we see here. We're going to introduce a third equation, though, that is valid only when we have a uniform field. So only when we have parallel plates or something that represents or is approximated by these two parallel plates. The third equation, the new one, looks like this. The electric field is equal to delta V over delta D. Now, this new equation that we've just learned, what do these variables mean? Of course, E is the electric field that's between these two parallel plates, the uniform electric field. Delta D, we got to be careful with this one. Delta D between these two parallel plates is not the distance that a charge has moved. We may not even have a charge in between the plates. There may not be an experiencer. This is like a producer equation, right? Except it's a producer equation for a uniform field as opposed to a non-uniform field like the other producer equation. So we may not even have an experiencer. It can't possibly be the distance that a charge has moved because there may not be a charge there. It is also not the distance from one plate to a charge or from the other plate to a charge, because again, we may not have a charge there to experience the field. Delta D rather represents simply the distance between the plates. It has nothing to do with the movement of a charge. It has nothing to do with the position of a charge. It has nothing to do with how far one plate is from a charge. It has everything to do with how far one plate is from the other, regardless of what's in between. Maybe there's a charge there experiencing the field, maybe there's not. Doesn't matter. Delta D is the distance between the plates, and it's of course going to be measured, like it always is, in meters. Now delta V, that's a little bit trickier. I'm going to loosely define that for you today, and then over the next couple of days, we'll refine that definition for you a little bit, okay? Delta V stands for the potential difference between the plates. Now, the units for potential difference are going to be V, volts. Delta V is capital V. V is also a capital V in volts. What that really means, at least the essence of what it really means, is the difference in energy per charge or per coulomb between the two plates. So we could say that you climb a hill. The difference in potential energy that you have between the bottom of the hill and the top of the hill is EP, right? Well, what's the difference in energy per kilogram? What's the difference in energy per kilogram of you? That's kind of analogous to potential difference. It's not the difference in energy of the charges between the two plates. It's the difference in energy per coulomb of charge between the two plates. Again, we'll talk about that a little bit more over the coming days. Right now, you just got to be able to recognize basically when you see that number, we plug it into this equation. I'm going to create a little Venn diagram actually that is going to hopefully tie these three equations together that we've learned over the last couple of days. The first one is going to be that producer equation, E is equal to KQ over R squared. Second one is going to be that experiencer equation, E is equal to F over Q. And the third one is going to be the new equation that we just learned, E is equal to delta V over delta D. We're going to make the first circle green. And when we draw that green circle around, that's going to represent the equations that are valid in a non-uniform field. If we know something about what caused the non-uniform field, of course, we're going to use this one. If we know something about what experiences a non-uniform field, we're going to use this one. The second circle that I'm going to draw is in red. These red ones are valid when we have a uniform field, something like parallel plates. This one is when we have information about what causes the non-uniform field, typically parallel plates. And then the middle one, of course, is valid when we have a situation where there's an experiencer experiencing the uniform field. Sometimes that middle one, sometimes I like to call that the universal equation, because that's valid whenever. As long as we have an experiencer, it doesn't matter what kind of field we have, whether it's a uniform field or a non-uniform field. It doesn't matter whether we have this with an experiencer somewhere in there, or it doesn't matter whether we have this with an experiencer somewhere in there. That middle equation is valid in any situation where we have an electric field, as long as we have something to experience that electric field. Here's an example. It says a cathode ray tube computer monitor. We don't even see these anymore, right? A CRT computer monitor. Everybody's got flat screen computer monitors. You can't even buy them anymore. A CRT computer monitor is like the TV that you see in the corner of the classroom here, this ancient, obsolete TV that you see up here. Cathode ray tube works by accelerating electrons across a big potential difference between these parallel plates. And ultimately, those electrons go through a little gap in one of the plates, hit the screen, cause the screen to glow. Okay, that's the picture that you see, is the glowing screen. Now, in this case, we have electrons that are going between two parallel plates that are 1.2 times 10 negative 2 meters apart, with a potential difference of 25,000 volts between them. We want to find the magnitude of the electric field between those plates. So how are we going to do that? Well, first of all, we want to take a step back from the question and do what we usually do when we see a question. What's going on here? What do we have here? Besides our givens, what do we have going on here? We have a situation where we have a uniform electric field. If we have a uniform electric field, then we're allowed to use the red equations here. the last two. We don't have an experiencer. There's nothing, we do have an experiencer. We have the electrons that are experiencing this electric field, but we don't know much about them. We know more about the plates themselves, about what's causing the field. So even though both of those equations in red are valid, we're going to use the second one, E is equal to delta V over delta D. Let's write down some givens, and then let's use that equation. The distance between the plates is 1.2 times 10 to the negative 2 meters. We know the potential difference between the plates is 2.5 times 10 to the 4 meters. And we want to find the magnitude of the electric field. This seems like a pretty straightforward question, especially since we already know which equation we're going to use. We know which equation we're going to use, not because of our givens. We know which equation we're going to use because we looked at the question and understood what was happening in the question. E is equal to delta V over delta D. Nick, question? That should be volts. The potential difference is in volts. 2.5 times 10 to the 4 volts divided by the distance between the plates, 1.2 times 10 to the negative 2 meters. We do the math there, we get 2.1 times 10 to the 6. What are the units for electric field? We said they were newtons per coulomb, or we could also say volts per meter now. Means exactly the same thing. 2.1 times 10 to the 6 newtons per coulomb, 2.1 times 10 to the 6 volts per meter. That's a pretty straightforward question, right? Right? I'm going to follow this up, though, with a little supplementary question. What's the acceleration of the electron that's experiencing this electric field? Don't look at my givens. Look at what's going on. Okay, we have a uniform electric field. What are we allowed to do in a uniform electric field? We're allowed to use the equation we just used, but we're also allowed to use this equation if we have an experiencer. Now we do. We have an electron. So let's do that. Let's say E is equal to F over Q. And let's rearrange that to solve for F. I get Q times E. 1.6 times 10 to the minus 19 coulombs times I think it was 2.08, wasn't it? 2.08 times 10 to the 6. Multiply those two together, we get an electric force that acts on the electron of 3.333 times 10 to the negative 13 newtons. And you guys learned the other day that if you're ever looking for acceleration, all you need to do is get the force and then divide it by mass. So we divide it by the mass of the electron. 3.7 times 10 to the 17. That would be meters per second squared, or you could say newtons per kilogram. Does that make sense? The question they gave us was really, really straightforward, right? The question that I followed it up with as a supplementary question, a little bit harder, okay, but it's still logical. Okay, we know what applies in a situation where we have a uniform electric field. Of course, the last two equations. And then look, F is equal to M times A always applies. Whenever something is accelerating, it always applies. Uniform, non-uniform, electric field, magnetic field, gravitational field, whatever. F equals MA always applies. So there we are. We're going to leave you for homework tonight with the two questions that we see on page 568. They're pretty straightforward. Okay, they're pretty straightforward. If you're looking for something a little bit more challenging, then I'll get you to take a look at the worksheet. I believe it's worksheet number maybe 9 on electric field between parallel plates, but I'm not assigning that as formal homework. There's a lot going on this week with the musical and basketball and so on, so it's not formal homework. This is your only homework. If you're looking for something a little bit more challenging though, take a look at that worksheet.